Hello everyone, welcome to Deeksha Karnataka YouTube channel and in your favorite series Brahmastra 2.0. Today I am going to discuss another important chapter, Moving Charges and Magnetism. So this is one of the most important chapters. There are chapters where you can get more than 10 marks from this chapter. So before I start, just have a look at the blueprint of the 2026 year. So 1 mark question will be one small answer type questions will be there, one small answer type 3 mark questions will be there, a long answer type questions, obviously one question will come, and total marks in this chapter is 11. So how many questions we are going to discuss in this lecture? We are going to discuss 15 MCQs, 5 fill in the blanks, 2 marker question 5, 3 marker question 5, and long answer type 5 questions. So this is our structure for today's lecture. So without much delay, let us start. A moving coil galvanometer can be converted into a voltmeter by connecting a low resistance in parallel with the galvanometer, a low resistance in series with the galvanometer, high resistance in parallel with galvanometer, high resistance in series with galvanometer. So for galvanometer to voltmeter, we need a high resistance in series with the galvanometer. So correct answer is option D. Now next question. The physical quantities related to magnetism are listed in column 1 and dimensions are listed in column 2. Identify the correct match. So here we have a dimension as well as some quantities and you have to match it. So magnetic field, then we have magnetic permeability, we have magnetic moment as well. Now you might be thinking, sir, this can be little difficult. So you have to remember that magnetic moment is given by current times area. So that is the matching for this particular thing will be magnetic moment into area. That means this is the matching for number 3. So number 3 with B. Let's see how many of the options are there. So even if you are not sure, you check if you know any one of them, and once you at least find one of them, see how many of the options are there with that matching option. So here number 3 with B is there only once, that is option D. Okay, so remaining matching is automatically done. Magnetic field is given by this, magnetic permeability is given by this, so option D must be the correct answer. Now next, before moving on, I just like to tell you that first of all, number 1, subscribe to this channel if you have not yet subscribed. We are going to do a lot of PU related and KCET related stuffs in our channel. So for that you have to first of all subscribe to our channel if you don't want to miss out in the competition. And secondly, if you want to download the lecture PDFs and all the updates that is happening in our channel, we also do some time to time we do some free giveaways. For that you have to join our WhatsApp channel. WhatsApp channel is link is given in the description section of this video, so don't miss out on any update. It will be helpful for you in a long term, so don't miss out on that. Join our WhatsApp channel immediately if you are already subscribed to the channel. Now let's move on to the next question. A charged particle small q is moving in an uniform magnetic field. The angle between the velocity v of the charged particle and magnetic field B is theta. The trajectory of the charged particle varies with angle theta. Match the following table by choosing the appropriate trajectory for different possible values of the angle theta. So the different angles are given and they asked you what will be the trajectory of the particle. Now we know that when the particle is moving along the magnetic line, that is the angle theta is 0, then it is a straight line. Okay, angle theta 0 is a straight line. Also we know that when the angle is 90 degree, it gives you the circle, right? So this is a circle. So only other match 45 degree must be helix. So anything between 0 and 90 gives you an helix. It does not necessarily to be 45 degree. It can be 30 degree, it can be 60 degree, it can be 31 degree. Any angle between 0 and 90 will always give you helix, whereas 90 degree will give you a circle and 0 degree will give you a straight line. So 1 is matching with B, 1 is matching with B, 2 is matching with C, and 3 is matching with A. So 1B, 2C, 3A. So correct answer option B. Right? Next, The Lorentz force is the force on a charged particle moving in a region containing both electric and magnetic fields. So Lorentz force is basically a force when both electric and magnetic field exist in some area, and the force experienced by the charge is given by the Lorentz force. Next, force on a charged particle moving in a magnetic field is maximum when the angle between the velocity of the charge and the magnetic field is. So force on a charged particle moving in a magnetic field is given by QVB sine theta. So when the force is maximum when sine theta is maximum. When sine theta is maximum, when theta is equals to 90 degrees, right? So correct answer is 90 degrees. Next, a charged particle is released from the rest at a region of uniform magnetic and electric field parallel to each other. The particle will move in a helix, in a circle, in a straight line, in a cycloid. Let's see. So we have a charged particle which was initially static. Now electric and magnetic field, they are parallel to each other. Okay, if you read the question, electric and magnetic field are parallel to each other. Okay, now if you release the charged particle Q, what will happen? Initially it was at rest, so definitely no force is acting on it. Now when you release it, what happens? The electric force is acting on it, that is given by Q into E, and because of this force it will accelerate in the direction of electric field. Okay, now because electric field and magnetic field, they are parallel to each other, then what happens is that magnetic field will not apply any force on this charged particle, because the angle theta in this case will be 0. We know that magnetic force is given by Q VB sine theta. Okay, because theta is 0, sine theta will be 0. So because sine theta is 0, magnetic force will be 0. So it will move in a straight line. Okay, the particle will move in a straight line because of the electric force, but magnetic force will be 0. In case they are perpendicular to each other, then it will be moving in a circle. Next, the path traced by a charged particle moving perpendicular to a uniform magnetic field is. So path traced by a particle moving perpendicular to the particle is QVV sine theta. Theta is 90 degree, so definitely it will be a circle. Okay, velocity and magnetic field, when they are perpendicular, then we get a circular motion. The dimensions of magnetic moment is, so what is magnetic moment? Magnetic moment is given by current into area. So current's dimension is A and area is L square. So L square means L square A is the dimension of magnetic moment. So L square A is the dimension. Next, a current flows along a length of an infinitely long straight thin walled pipe, then the magnetic field is. This is a question from one of your previous year, I think 24. So I flows along a length of an infinitely long thin walled pipe. So the thin wall is very, very thin. Okay, and it's a pipe. Pipe means internally it is hollow. Okay, externally it has some thickness. The pipe wall is very, very thin. Okay, now what is the question? Then the magnetic field at all the points inside the pipe is same but not 0. At any point inside the pipe is 0. Is 0 only along the axis of the pipe, is different at different points inside the pipe. So we are considering any point inside the pipe. So inside the pipe, if you observe that because the wall is very, very thin, if you consider a loop, and if you construct the loop and apply Ampere's circuital law, B dot dl, you will see that mu naught current enclosed through this area is equals to 0. So it will be mu naught 0. So B dot dl will be 0 and dl cannot be 0. So only thing is B should be 0. So magnetic field inside this thin walled pipe, whenever you consider a pipe or a shell, okay, magnetic field will be 0 because of Ampere's circuital law. Okay, so at any point inside the pipe it is 0. Next, parallel currents dash and anti-parallel currents dash. So parallel currents attract, anti-parallel currents repel. So parallel currents attract, anti-parallel currents repel. So correct answer is option C. A planar loop carrying a current I having n closely wound turns and area A possesses a magnetic moment M, where M is equals to NIA. So normally it is IA for one loop. For one loop it is IA, but if there are n number of loops, then it will be NIA, National Investigative Agency. Okay, so it is the answer M. Next, a charged particle moving in a circular path in a uniform magnetic field, then choose the wrong statement among the following. So that means here we have three correct statements, only one of them is incorrect. Radius of the circular path varies directly with its velocity. Radius of the circular path varies inversely with the magnetic field. Frequency of the revolution varies directly with the charge. Frequency of the revolution varies directly with the kinetic energy of the charge. Let's see. So we know that whenever there is a charge moving in a circular path, there has to be a centripetal force, which is given by mv square by r, and from the Lorentz force we know that it is given by qvb sin theta, and for circular motion theta is 90 degree, that means sin theta is 1. So from here we can calculate the radius first. So radius, obviously one of the v is cancelled, and we get r equals to mv by qb. So we can see that radius is directly proportional to velocity, and radius is inversely proportional to 1 upon magnetic field. So both statements are true. Okay, it is radius varies directly with velocity and inversely with magnetic field. Both statements are true. Now we have to calculate the frequency of revolution. Frequency of revolution means omega, angular frequency. Okay, and even if you try to calculate normal frequency, it is same, because omega is equal to 2 pi f, so it does not matter. Okay, so frequency or angular frequency is same. So how to calculate that? Now mv square by r can be written as m omega square r. Okay, and that is given by m qvb, sorry, not m, qvb. Now v is given by r omega. Okay, v is given by r omega. So let's put that q into r omega b. So r cancels, one of the omegas cancelled, and we get omega equals to qb by m. Omega equals to qb by m. So now see, frequency of revolution varies directly with the charge. So frequency of revolution is directly proportional to the charge. So this is a correct statement. Frequency of revolution varies directly with the kinetic energy of the charge. Now if you see that nothing is related with kinetic energy over here, that means this is a wrong statement. Wrong statement means this will be the correct answer for our question. Okay, now next question. An electron is traveling horizontally towards east. A magnetic field is vertically downward direction exerts a force on the electron along. So the electron is traveling along the east direction. Okay, and our north is not along upside, north is along this side, and south is along this side. Obviously, if you see north, east, south, and south, east, west, north. So if you are familiar with this, it is actually not upward direction. Upward is different. Okay, so this is our upward direction. This is our downward direction. Okay, this is east, this is west, this is north, this is south. Okay. Now what they said, that the particle is moving, the electron is moving in the east direction, and a magnetic field is acting in the downward direction. So what will be the direction of the force? So we know that from Lorentz force, force is given by Q into V cross B. V is first, B is second. So if you first, how to find a cross product? To find the cross product, what you have to do? You have to first align your fingers in the direction of electric field. in the direction of velocity first. So velocity is along east direction, and then you rotate your fingers towards the second vector, which is magnetic field in this case. So in this case it will be downward. Okay, so downward means the other direction must be into the page of the paper, that is north. So it will be along the north direction. Be careful if you see such questions. Draw the diagram properly and understand that it is V cross B. So first will be in the direction of V, cross product principle. So first you have to align your fingers in the direction of first vector. Order of cross product is very, very important. Okay, if it is V cross B or B cross B, based on that direction will change. So V cross B means first you point your fingers in the direction of the first vector, and then you curl your fingers towards the second vector. Then your thumb will point the direction of the resultant vector. Okay, so this is the resultant vector in this case into the page of the paper. Okay, so north is the correct answer. Next, the resistance of an ideal voltmeter is infinity. Resistance of ideal voltmeter is infinity. Resistance of ideal ammeter is 0. In a moving coil galvanometer, a current I produces a deflection theta. Then I is proportional to tan theta, I is proportional to theta, I is proportional to theta square, I is proportional to square root of theta. So if in a moving coil galvanometer a current I produces the deflection theta, then it is proportional to theta. Okay, the small angle approximation, I is always proportional to theta. Next, fill in the blanks. When the charged particle move in a combined magnetic and electric field, then the force acting on it is known as. So when the charged particle moves in a combined electric and magnetic field, the force is known as Lorentz force. So correct answer must be Lorentz force. Let's see the answer. Yes, the direction of the magnetic field due to a current loop is found using the, so direction of magnetic field due to a current loop is found using the right hand thumb rule. It is called right hand thumb rule. So if this is a current carrying loop and the direction is given by this, then how can you find the direction of magnetic field? Curl your fingers in the direction of magnetic current, then your thumb will point towards the magnetic field. So this is called right hand thumb rule. Let's see where it is. Right hand thumb rule, this is the answer. Next is the alternative form of Biot-Savart law is Ampere's circuital law. So if you have watched any of my KCET lecture, there I have discussed that Ampere's law and Biot-Savart's law, they are actually the same. Only thing is Biot-Savart's law is more general. Ampere's law is some cases can be tricky if you if the line is not symmetrical. You can apply Ampere's circuital law as well, but it can be tricky if the line is not symmetrical. Okay, so Ampere's law and Biot-Savart's law are almost similar. So Ampere's circuital law is the answer. Current carrying circular coil is equivalent to a magnetic dipole. Okay, current carrying circular coil is equivalent to magnetic dipole. The north pole is formed like this and the south pole is on the opposite side. Okay, so it is a magnetic dipole. Resistance of an ideal voltmeter is infinity. Resistance of a ideal ammeter is 0. So correct answer is infinity. Okay, done. Now let's move on. A long air core solenoid of 10,000 turns per unit length carries a current of 2 ampere. Calculate the magnetic field at the midpoint on its axis. Now from this chapter there is a tendency that a 2-marker numerical question will come, very simple, easy numerical. So let's solve it. So long air core solenoid, 1000 turns per unit length, carries a current of 2 ampere. Calculate the magnetic field at the midpoint of this axis. What is the formula? Magnetic field inside a long solenoid is given by mu naught Ni. Okay, mu naught Ni. What is the value of mu naught? Mu naught is 4 pi into 10 to the power of -7. Remember, it is mu naught, not epsilon naught. Epsilon naught's value is different, mu naught's value is different. Okay, number of turns per unit length is given by 1000 and current passing through is 2. So now let's simplify it. We get 4 to the 8 pi into 10 to the power of -4. Now you can leave the answer over here, or you can multiply 3.14 and you will get approximately 25 into 10 to the power of minus 4 Tesla. Okay, approximately this will be the answer. In this case I have kept it 8 pi, but 25 is also acceptable. Now let's move on. A moving coil galvanometer gives a deflection of 10 divisions when 200 microampere of current passed through it. Find the current sensitivity of the galvanometer. So this is a very easy question. Okay, number of divisions divided by current. Okay, 10 divisions divided by 200 microampere, it will be 10 into 10 to the power of plus 6 divided by 200. Why 10 to the power of plus 6? Because microampere means, if you are confused, then let me write it one more line. So microampere means 10 to the power of minus 6, so this will go up and you will get 10 into 10 to the power of 6 by 200. Now one important thing about current sensitivity, 10 into 10 to the power of 5 by 20, so it will be 5 into 10 to the power of 4 division per ampere. Now in some cases it might be given in the unit of ampere per division, so both are okay, ampere per division or division per ampere, but unit, if you are mentioning, you have to mention the units. So here it is given is 50 divisions per ampere. I think there is some mistake. It is microampere, not milliampere, but it will be 10 to the power of 4 division per ampere, not 10 to the power of not 50. Okay. Now next, when does current carrying conductor placed in a uniform magnetic field experiences maximum force, minimum force? So what is the expression for force acting on a straight current carrying conductor? The expression for force on a straight current carrying conductor is given by BIL sin theta. Bill. Okay, remember bill. Okay, you are paying monthly bill. I used to, when I was a student, Bill Clinton was the president of America, so you used to remember Bill Clinton. Okay, I think a few years back, before I studied, Bill Clinton was president, so he was famous for some, like today, nowadays, Trump is famous. So back in the day, Bill Clinton was also very, very famous person. So we used to remember by this, Bill is correct, and Bill sin theta is the correct formula. Now, when will be the force will be maximum? The force will be maximum when theta is equals to 90 degrees. So when theta is 90 degrees, force is maximum. When the force will be minimum, when theta is equals to 0 degrees. Okay, that's it. So you just need to mention the formula and explain that when theta is equals to 0, sin theta will be 1. Okay, when theta is 0, sin theta is 0. That means force will be BIL, and in this case force will be 0, minimum force, right? Let's move on. Write the expression for magnetic force per unit length between two long straight parallel conductors carrying current. Give the nature of the force between two parallel conductors carrying current in the same direction. So the expression for force per unit length is given by mu naught by 2 pi Ia Ib by D. Now you have to mention mu naught equals to Ia equals to, okay, Ib equals to, and D equals to. You have to mention these quantities, and then you have to mention parallel currents attract and anti-parallel currents repel each other. So without this explanation, you will not get one full mark. They will deduct 1 mark for if you don't explain the terms. Next, a galvanometer has a resistance of 12 ohm and meter shows a full scale deflection for current of 3 milliampere. How will you convert this into a voltmeter of range 0 to 18 volt? So whenever you see such kind of questions, you have to take the maximum value of the voltage. Maximum value of the voltage is very, very important. So here we have a galvanometer, and the maximum current that it can withstand is given by 3 milliampere. The resistance of the galvanometer is 12 ohm, Now you are trying to convert it into a voltmeter. What is the basic process of converting into a voltmeter? The basic process is to add a high value resistance in series. So that's what we will do. Now remember that no matter what, the maximum current through the galvanometer cannot exceed this milliampere rating, whatever rating of the galvanometer. This is the maximum allowed current through the galvanometer. Okay, and if you are trying to measure 18 volts through this galvanometer, that means when 18 volt is applied across this galvanometer, when 18 volt is applied across this combination of the system, then the current in the circuit will be 3 milliampere. Okay, the maximum value, not for any other value, the maximum value of the voltage when you apply, the current should be the maximum as well. Similar thing goes for ammeter as well. When maximum current is being passed, the current through the galvanometer should be the maximum range that is given. Okay, here 3 milliampere is given, so that means 3 milliampere should be the range, or 3 milliampere should be the value of the current that is being passed through the galvanometer, right? Now what we will be doing, we will apply the law, Ohm's law. So what is the total resistance? Total resistance is R plus 12. What is the current through it? Current is 3 milliampere. Milli means 10 to the power of minus 3, and that should be equals to the voltage that we have applied, and we said that maximum voltage gives maximum current, so this must be the applied voltage. Now we have to simplify it. 3, 6, 18. So you got R plus 12 equals to 6 divided by 10 to the power of minus 3, or 6 into 10 to the power of 3, or 6000, or R equals to 6000 minus 12, that is 5988. Simple question, simple answer. 5988 ohm is the resistance that you have to connect in series. So you have to mention that in series. Okay. Next, state and explain Biot-Savart's law with a suitable diagram. So what is the diagram that you have to explain? You have to draw a diagram. Okay, a wire carrying current I. Okay, you take a small element dl, then you are trying to find the magnetic field, say at a point P, and if you take this angle will be theta. Okay, this is the direction of this element dl, and the distance between this point is small r. Then Biot-Savart's law states that the small magnetic field due to this element at point P is directly proportional to the amount of current that is being passed. dB is directly proportional to the length. dB is directly proportional to angle theta, sine theta, and dB is inversely proportional to square of the distance. And combining everything, we can write dB equals to mu naught by 4 pi I dl sine theta upon r square. Okay, this is the formula for Biot-Savart's law. Now next, derive an expression for angular frequency of revolution for a charged particle moving in perpendicular to the uniform magnetic field, or obtain an expression for the radius of the circular path taken by a charged particle moving in a perpendicular to the uniform magnetic field. Now we have solved both of them. We will be doing again. So what is the starting point? Starting point is the magnetic force is given by QVB. Okay, QVB is the magnetic force. Now sine theta is obviously 1, and whenever it is rotating in a circular path, there has to be a centripetal force which is given by mv square by r. Sometimes this is also written as m omega square r. Okay, m omega square r we will be using for the first part, and this one we will be using for the second part. Now let's see. First is expression for omega. For omega. Okay, now how to calculate that? So at equilibrium these two forces must be equal, so FB must be equals to FC, so we can say QVB equals to M omega square C, omega square R, sorry, M omega square R. Now V for a rotational motion is given by R omega into B equals to M omega square R. Now R cancels, and if you simplify QB by M equals to omega square by omega, or one of the omegas cancel, so omega is equal to QB by M. This is the correct formula for angular speed. Now what about radius? Radius is easy, just compare these two forms. So QVB, so now it is expression for R. Okay, QVB equals to MV square by R. So just R comes over here and remaining goes to that side, so MV square by QVB, one of the V's gets cancelled, so MV by QB. So R equals to MV upon QB. So this is the correct formula. Okay. Now next, what is Lorentz force? Write an expression and explain the terms. This is one of the most common question from this chapter. 2 marker, 3 marker, both question might come. Force acting on a moving charge particle in the presence of an electric and magnetic field is called Lorentz force. Okay, in case of 2 marker question, they will ask you write the formula and explain the terms. In case of 3 marker, they will also ask what is Lorentz force. So this statement is only for 3 marker. For 2 marker, this formula and this expression is compulsory. So F is equal to Q into E plus Q into V cross B. Q is charge, E is electric field, V is velocity of the particle, B is the magnetic field. Next, how can a galvanometer converted into a voltmeter? Explain with diagram. So voltmeter should have a very high resistance as it is connected in parallel to the circuit. A galvanometer is converted into a voltmeter by connecting a suitable high resistance in series with the with it. This way the overall resistance of the galvanometer remains high. So we have to connect a very high value resistance with series with the galvanometer so that the overall resistance remains high. And if current through the galvanometer is given by Ig, the voltmeter is measuring a voltage V, then V equals to Rg plus R into Ig. Okay, this is the voltage that you measure. Okay, this simple equation, if you write it, you will get full marks. Next, how a galvanometer be converted into an ammeter? Explain with the terms. Now among these two questions, galvanometer to voltmeter came the most in the past. Galvanometer to ammeter came a little bit less, but this is also very, very important. An ammeter should have a very low resistance as it connected in series in the circuit. This is achieved by connecting a suitable low resistance S in parallel called shunt with the galvanometer. This way the overall resistance of the ammeter remains low and the galvanometer is converted into an ammeter. So if you see the diagram, this is the diagram for galvanometer to ammeter. Here we have connected a low value shunt in parallel. Okay, now this is also very, very important. You have to find the value of this current Ig, that the current and the total current I. So this is I minus Ig. So you have to find the current I. I is the current that you are measuring, and you have to calculate this current I in terms of Rg and Rs. So how to do that? So voltage, they are connected in parallel, so voltage across this should be voltage across this. That means Ig Rg should be equals to I minus Ig into Rs. Okay, or don't calculate Ig only, okay? You have to calculate I. Remember that. You have to calculate I, not Ig, because ultimately you are measuring this current, not this current. This current is already known for a given galvanometer, okay? So Ig, Rg plus Ig, Rs equal to I, Rs. So I equals to Ig into Rg plus Rs divided by Rs. Okay, if you know this, if you can remember this expression, very good, you can directly write this expression. If you don't remember this expression, you have to start from here. Remember, the voltage drop across the galvanometer is same as the voltage drop across this small resistor. Okay, so these are all the 3 marker questions. Now let's move on to the 5 marker questions. State Ampere circuit law. Now from this chapter, numerical questions do not come. We are expecting a full theoretical question from this chapter. State Ampere circuit law and arrive at the expression for magnetic field due to a long straight current carrying wire. So Ampere circuit law is statement is current through any closed loop is given by B dot dl if a current passing through a closed loop is I and magnetic field along the closed loop at any point is B, then B dot dl equals to mu naught I. You have to write the statement. I am not writing the statement. Statement you have to write. Okay, if you want to if you want my help to write the statement, you can tell me in the comment below. Otherwise, statement is very standard. Only thing that you have to do, you have to mention the statement and write the mathematical term as well. Now, for a very infinitely long straight wire, let us we are trying to find the magnetic field, say at a point P. We will construct a circular Amperian loop. Circular Amperian loop of radius r. So these are the very important thing the students do not write. If you don't write it, you will lose some marks. Okay, circular Amperian loop of radius r across the wire. Now if we apply Ampere circuit law, then we will see that B dot dl equals to mu naught I. I is the amount of current that is being passed through this wire. Right now, if you see that this is a circular wire, that means it's a symmetrical. Circle is one of the most symmetrical two-dimensional object. Right? So any point on this circle, if you consider the distance should be same distance from on this side, same distance on that side, same distance this side and that side. Okay, all sides, not only this and that, all points on this circle will be at equal distance from this wire. Okay, that means it is a circular symmetry. So if there is a circular symmetry, that means the magnetic field has to be constant along the line joining along the curved line, right? So what we will be doing, so magnetic field is constant, so we will magnitude wise we will take that out and we will say B into dl. Okay, mu naught I. Now what is this weird symbol? Integration we know. What is this? This represents close integration. Okay, I told you in the Gauss's law chapter as well. This represents closed integration. Closed integration means your starting point and your ending point. If you start say at this point, after rotating the entire circle, if you again end at this point, then this is called a closed integration. It can be due to a surface, it can be due to a line, it can be due to a curve. Okay, but normally if the line is open, it is not possible. If it is a curved line, okay, starting and ending point can be closed, then only close integration is possible. Not every case you can consider a close integration. That's why in case of Gauss's law also, in case of Ampere's law also, in Gauss's law surface must be closed. In case of Ampere's law also, the loop must be closed loop. Open loop does not applicable for Ampere's law. So close integral dl means basically if you take small portions, dl, all dls if you take and if you add them, that gives you the close integration. Integration means basically some kind of addition. Okay, integration is a type of addition. Okay, so if you take small portion of this entire loop and if you add them, you will get the close integration dl. So what is the meaning of small portion? If you add all the portions of a circle, what do you get? You get the perimeter of the circle. So perimeter of the circle is what? Perimeter of circle is given by 2 pi r, and that is equals to mu naught I. Okay, so close integration dl is basically the perimeter, which is equals to 2 pi r for a circle. Okay, now from here you can calculate what is b. So b will be equals to mu naught I by 2 pi r. Now we can write it in little bit civilian way, mu naught by 4 pi I by 2I by r. Okay, this expression is similar to that of a straight wire, charged wire. Remember, 1 by 4 pi epsilon naught, 2 lambda by r. Similarly here also mu naught by 4 pi I by r, 2I by r. Okay, you can have 2 pi over here, and you can cancel 1 2, but this is a standard way of writing. You can write, you can leave the answer in the previous form also, you will get full marks. Next, derive the expression for magnetic field at a point on the axis of a circular current carrying loop. Now for your year there is a possibility that this will not come, but there is no guarantee. What I have seen from the past few years of paper analysis, this generally comes alternate years. Okay, this generally comes alternate year. This derivation came last year, so there is a less chance it will come for your year. Your year, the next derivation is important. Anyway, no harm in practicing, and that is for board exam, by the way. For your pre-board exam, this question might come, and it is an important question. So in some of your cases in pre-board exam, this question will come definitely. Not every one of you, but some of you this will come. Okay, so the radius is given by r, and we are trying to find magnetic field at some point, say p, at a distance x. Okay, we will consider a small element over here, and what is the distance of this element from this, say small r. From Pythagoras theorem we can write this distance as capital R square plus x square. Okay, now we will apply, what we will apply? We will apply Biot-Savart's law. Okay, Biot-Savart's law states that the magnetic field due to a small element is given by I dl sin theta upon r square. Now here this theta is the angle between the top portion of the loop, that is this one, and the distance vector, which is actually 90 degrees. Okay, so this angle and this is 90 degrees. So this theta is 1. So dB will be I dl by r square. Sin theta is 1. But this is not it. If you consider what will be the direction of the magnetic field, the direction of the magnetic field will be along some direction like this. Okay, and this angle, if this angle is phi, then this angle will also be phi. Okay, this can be proven geometrically. I am not doing it. So this angle is phi, this angle is phi, because we are not getting any marks for this derivation. So you see that there will be two components. One will be along the y direction, one will be along the x direction. So this will be dbx and this will be dby. Now if you consider a diametric opposite point, then the magnetic field will be in this direction. Again there will be an x component, there will be an x component, there will be an y component. So as you can see, for each and every point there will be a diametric opposite point. So that means the y components will cancel each other. Eventually only thing that we will be left with is the x component. So y component will not play any role, only the x component will play a role. That means the net magnetic field will only have x component, which is given by dB cos phi. That will be given by dB cos phi. So what is the value of that? So dB, so if you consider this angle, cos phi is given by base by hypotenuse. So base is r and hypotenuse is small r. Okay, now we will put these values over here, and we got there was one thing I missed I forgot, mu naught by 4 pi was there. Okay, so mu naught by 4 pi. Okay, and we have I dl r divided by r square. Initially was here, there was one small r, another added, so it will be r cube. Okay, so this is the magnetic field due to this small element. Now why we are only calculating x component? Because if we when we do the sum of all the components, when we take the integration of this, y components will cancel. That's why we are only considering the x component of the combination. So what will be the total magnetic field? Total magnetic field is integration of dbx. Again, it's a closed integration because circular path, so you have to take start and end at the same point. So it will be again a closed integration. Now when you are doing a closed integration, mu naught by 4 pi I r cube, everything is constant except this small dl. So that will be only left. So mu naught I r by 4 pi small r cube integration dl, close integration dl. Now what is close integration dl? We already explained. Close integration dl is nothing but the circumference of the circle, so it will be mu naught I r. So mu naught I r divided by 4 pi r cube times what is the circumference of this circle, that is close integral dl, that is 2 pi capital R. Don't make any mistake, it will be 2 pi capital R. So 2 pi will be cancelled and we got our result as mu naught I r square. 1 r was here, 1 r is here, so I r square divided by 2 r cube. But this is not the final answer. You have to substitute the value of r over here. R is square root of r square plus x square. That means r cube must be equals to r square plus x square to the power 3 by 2. Why 3 by 2? By 2 represents the square root and this cube represents the cube. So we have to put that value as well. So we got, after little bit rearrangement, mu naught by 2 I r square divided by capital R square plus x square to the power of 3 by 2. So if you see that in my entire derivation I have used this expression at the end, but I have seen students, they start using this from the beginning and somewhere in the middle they lost and they make some unnecessary error in this expression. Okay, so don't do that. Use this way your derivation will be cleaner, smaller and lot less error free. Okay, so a lot less error. Okay, so errorless derivation is important, so that's why you have to do this like this way. Now next, derive an expression for force per unit length on two infinitely long thin parallel straight conductors carrying current and hence define ampere. Now this question is important for your particular this year, for your board exam. Okay, almost every alternate year this question and the other question are coming, but with a pinch of salt, this is not guaranteed, as I mentioned. Okay, this my intuition tells that this question is important for you. Yeah, so you have to practice both this one and the previous one. Okay, all the other ones are did came in the past once or twice, in especially the second and third papers, improvement papers or supplementary papers, but these two are predominantly the main question for your PU board papers. Now let's see. Here we have two parallel wires, 1 and 2. Okay, now if we want to consider this wire, say wire I carrying a current I1, This is a wire 2 carrying a current I2. Both of them are carrying current in the same direction. We are assuming for now. The distance between them is D. Okay, so if I want to find the magnetic field due to this infinitely long wire at this junction, at this point, what will be the magnetic field? The magnetic field due to wire 1 at the location of wire 2 is given by, we just did the derivation by the way, it is given by mu naught by 4 pi 2I by R, or here we will not use this symbols, we just to remember it I used it, so I by D, I1 by D. So this is the magnetic field of wire 1 due at the location of wire 2. Okay, this is the magnetic field of wire 1 at the location of wire 2. Now what will be the force acting on this wire 2 due to this magnetic field? For that, what you have to do, you have to consider a length, because magnetic field infinite wire does not work. You have to consider a length of the second wire. Okay, suppose we are considering a length of L, then the force is given by force on 2 due to 1. Okay, force acting on the wire 2 due to first wire is given by B IL sin theta. Now theta here is 90 degrees, so only BIL, so it will be mu naught by 2 pi I1 by D into I2 into L, or mu naught by 2 pi I1 I2 by D into L. Now this equation is very symmetric. What is the meaning of that? If you swap the location of 1 and 2, this expression will not change. So if you do the same process for the wire 2 at the location of wire 1 and then calculate the force acting on wire 1 due to wire 2, you will get the same expression. So you can write similarly. Why you can write similarly? You have to understand these small points. Okay, if you understand it, it will save some time for you during the exam. Not always you can write similarly. Okay, some cases you can write similarly if it is actually similar. So for example, in this case it is similar because if you swap the location of I1 and I2, the expression does not change. So F12, so F21 is, first is coming 1, second is 2, so F12 will be again the same thing, mu naught by 2 pi I2 I1 by D into L. Okay, so this is the force. So or again you can write 2 pi, now I2 I1 is same as I1 I2 by D into L. So this is the force. Now vectorially F12 is exactly opposite of that F21. So if this force is trying to pull it in this direction, then this force will try to pull it in this direction. So this is F on 2 due to 1, this is F on 1 due to 2. Okay, so if you apply this logic, okay, they are in the opposite direction, but magnitude wise F12 equals to F21, and say that is equals to F. Say this is F. So what is the value of F? F is given by this expression, mu naught by 2 pi I1 I2 by D into L. Okay, now L here we have assumed because the wires were infinite, right? So this L actually has no meaning. For that, what we have to do, we have to find the force per unit length. Force per unit length is given by F by L, which is given by mu naught by 2 pi I1 I2 by D. This is the expression for force per unit length due to two current carrying wires. Now here also, this is not the end, you have to also define the term ampere. Okay, so how to define ampere? To define ampere, if I1 equals to I2 equals to 1 ampere, D is equals to 1 meter, then the force will be given by mu naught by 2 pi. Now mu naught is 4 pi into 10 to the power of minus 7. So if you put that value, you will get the value of the force per unit length will be given by 2 into 10 to the power of minus 7. Okay, Newton per meter. Okay, so that is how we define ampere. So ampere is the current when flows through each of the two parallel conductors kept at a distance of 1 meter. So I1 and I2 both are equal to 1 and this distance is equals to 1 meter. Then the force is 2 into 10 to the power of minus 7 Newton per meter. Okay. So what is the meaning of this? The meaning is if I1 equals to I2 equals to 1, D is equals to 1. So they are actually 1 ampere and this is equals to 1 meter. Then force per unit length is mu naught by 2 pi. So what is mu naught by 2 pi? Mu naught is 4 pi into 10 to the power of minus 7. So mu naught by 2 pi will be 2 into 10 to the power of minus 7. Okay, 4 pi by 2 pi, only 2 left. Okay, so this is how you can define ampere. This is a way to define ampere. From this formula, the definition of ampere came in the existence. That's why this is very important. Now let's move on. With the help of a diagram, derive the expression for torque on a rectangular current loop placed in an uniform magnetic field. So we have a rectangular loop, current carrying loop, carrying a current I. We have a magnetic field here, say north, and we have magnet over here, say south. So magnetic field lines are passing like this. Okay, current is here, current through this is here. This is current, this is the current. Now here, whenever a current loop is placed in a magnetic field, it will experience as a torque. Now how to calculate that torque? Suppose the length of this loop is given by A and breadth is given by B. Okay, breadth is given by B, length is given by A. So the current through both of the wire part is I. Now whenever you place a current carrying wire in a magnetic field, it experiences a force. What is that force? That force is given by BIL sine theta. Okay, BIL sine theta. Now if you see that for the wire, say this is 1, say this is 2, this is 3, this is 4, 4 sides of the rectangle. For wire 1 and wire 3, for wire 1 and wire 3, the angle, for this case angle theta is 0. This case theta is 0 and this case theta is 180 degrees. Now if theta is 0 or 180 degree, both cases it will be 0, right? Sine theta 0 is 0, sine 180 degrees also 0. For this case angle is 90 degree, this case also angle is 90 degree but in the opposite direction. So in one case there will be a torque in the upward, there will be a force in the upward direction. For the other case there will be a force in the downward direction. Okay, so basically if you consider this is your rectangular loop, these two sides are parallel, that means parallel or anti-parallel, there will be no force on these two wires. Only force that will act along this wire and this wire. Okay, so in this case this will be upward and this case it will be downward. Okay, so sine theta is 90 degrees, so the force is only BIL sine theta. Okay, and what is L in this case? L is A. So force on any one of them is given by BI small a. BI small a, but this is force on both cases. So this is F4 and F2. F on 4, F on 2. Okay, so F on 4 and F on 2 both will be BIA. Right, so this is the force acting on these two wires due to the external magnetic field. Okay, now what will be the torque? So when two equal and opposite force acts on a system, but at a different point the system experiences a torque. So what is the value of the torque? Value of the torque is any one of the forces, any one of these forces, we are using F commonly, times times the distance between the forces. What is the distance between these two forces? So this force is acting along this line, this force is acting along this line. So what is the force between the distance? Force between the distance is B. So F into B. Now put the value B I A B. Now what is AB? So this is a rectangle. Rectangular length is A, breadth is B. Length into breadth gives the area of the rectangle. So it is B I A. So this is the torque acting on this particular loop. Now if the loop contains more than one turn, then the torque will be N into B into I into A. Okay, N B I A. Okay, or to remember the formula, this is a way. Okay, Nayab. Okay, Nayab is a Hindi word or a Urdu word which means very rare. Okay, so Nayab is the term that you can remember. This is how you can do the derivation. This is a very simple derivation, and if this derivation is coming, along with that there will be one more question like state the Ampere's law or state Biot-Savart's law. There will be one more question associated with this. Otherwise this is a very simple and easy derivation. Okay, so Nayab is the formula, but this formula we'll be using in our next question as well. What is the next question? What is the principle behind working of a moving coil galvanometer? With the help of a neat level diagram, obtain the expression for angular deflection produced in moving coil galvanometer. So this is the neat level diagram. Okay, everything is same. Only thing is that here we have a spring. Principle: when a current carrying coil is placed in an uniform magnetic field, it experiences a torque. What is the expression of the torque? Expression for the torque we have already calculated. NIAB is the expression for the torque which is acting on this coil. Now this torque, what is the role of a torque? What does a torque do? The torque always try to rotate. Right? If you apply a torque on a static object, then it will try to rotate the object. Okay, so if this is left unchecked, then the galvanometer coil will keep on rotating. But to keep it in check, we apply a spring. That spring will try to resist this rotation, and it will actually stop the rotation after some time. And if the angle of deflection of this is given by theta, then the moment of inertia of the coil times the angle of deflection theta, okay, can be given by Nayab. Now in this particular case, if you apply the spring constant, that will also be fine. Spring constant K. Torque is given by I theta. Okay, in this case it will be K theta. Theta is the deflection. Okay, theta is the deflection, and K is the spring constant. Okay, from here we can say that theta or the deflection of the galvanometer, theta is the deflection of the galvanometer, is given by NIAB by K. Okay, or theta equals to NBA by K into I, or theta equals to G into I, or G is NBA by K is called the galvanometer constant. Very simple and easy derivation, nothing much. Okay, so theta is proportional to the current, so more current passing through the galvanometer, more deflection it will be giving. Okay, so this is the simple and easy derivation. It came once or twice, and it came once in the third paper of the second or third paper, means improvement or supplementary papers. Okay, it did came but main paper I think it came only once. This derivation never came in the main paper, but it came in the supplementary papers once or twice. Similarly, this also came only once in the main paper, and in the supplementary paper it came 2-3 times. Okay, so maybe it will come in your exam, but as you can see, the derivations are easy. If you practice it once, you should be able to remember it. Main important derivation is this one. This is little tricky and long derivation. This one is also tricky and long derivation. So these two derivations you have to practice 2-3 times, and also you have to remember this definition of Ampere. These derivations are easy. Diagram and derivation should not take much more than 5 minutes of your time. So if you see any other question, sometimes students feel depressed that okay, whatever I have studied throughout, it did not came. But if you are a topper, if you are preparing for out of out, then definitely you have to practice other questions than the main questions as well. Okay, so this is the end of this lecture, and if you have any doubts, any questions, please mention that in the comment section below. I'll try to answer as many of them as possible. I'll be back with a new chapter very soon. Till then, bye.